And the correct answer is false. Okay, this will only be true if it has the same charge. If the charge changes, the energy changes. So in other words, the electric potential is not the same as electric potential energy. And a good example is just batteries. So voltage, again, is potential energy per charge, whereas the actual energy is what's stored inside the battery, which we can find by multiplying voltage by charge, or QED. So long story short, here's what's weird. When you buy batteries in the store, you can buy all sorts of sizes and shapes. You can buy a D cell battery, a C cell, a AA, a AAA, or a 9-volt battery. Here's what's nuts. Technically, a D cell, a C cell, a AA, a AAA battery, they're all 1.5 volts. If we were to ask, well, which battery has the highest electric potential? The answer is the 9-volt battery. Electric potential is just a fancy way to say voltage. The 9-volt battery has the highest electric potential. These guys all have 1.5 volts. So using our gravity analogy, this would be like going up to the 9th floor of a building or a ski hill that's 9 stories tall. Whereas these batteries all raise you to a potential of 1.5 stories, a little bunny hill that's only 1.5 stories tall. So why do we have different size batteries that have the same voltage? So if you think about it, the reason why is some electronics you don't want huge batteries for. So for example, a TI calculator is usually powered by 4 AAA batteries, which would then raise the voltage inside the circuit 1.53, 4.5 to 6 volts. Whereas something that's bigger, like a flashlight, a radio you bring to the beach, would be powered by D cell batteries. And technically, if I had 4 D cell batteries, it's also only 6 volts. So what's the advantage of having a bigger battery? Well, the answer is a bigger battery can store up more energy. So the D cell doesn't necessarily have more voltage. It has the same voltage as a AAA battery, but it has more potential energy stored in there. There's more chemicals in there, more metals. We can store up more charge. So in other words, it will run things like flashlights, radios, speakers when you're at the beach for a longer period of time. So one crazy thing is you could soup up your calculator. Instead of running it off 4 AAA batteries, you could put on a special box and wire it up to run off 4 D cell batteries, which would be crazy because now your calculator would weigh like 2 pounds. But instead of having to change the batteries every few months, your calculator might run off 4 D cells for like 3 years, which would be crazy there. Finally, we have one last energy example problem. Check your understanding here. Question reads, how much energy is needed to move one electron through a potential difference of 9 volts? So let's go ahead and break this down to help you solve this here. So the first thing is, make a little sketch. In this case, picture's not that helpful. It's just a battery. There you go. 9-volt battery. No biggie. Just trying to keep good habits here, right? Next, step 2, let's break down the knowns and unknowns. So in terms of what we know and don't know, we're trying to figure out the energy. And in this case, it's recognizing it's the potential energy, the electric potential energy stored inside this battery. And then we're given only 2 pieces of information. The voltage is 9 volts, the electric potential, and then the charge of an electron is given, and it's a hidden piece of information because we have to know that the charge of an electron is 1.6 times 10 to the negative 19th coulombs. For step 3, which is to write out the equation that relates our knowns to unknowns. So in this case, I want to know PE, I know V, I know Q. So the only equation that works is the voltage equation. V equals PE divided by Q. So now we can solve by substituting in. So to find PE, we're just going to multiply volts times coulombs. 9 volts times 1.6 times 10 to the negative 19th coulombs will give us 1.44 times 10 to the negative 18th joules. So in other words, the whole point of a 9-volt battery is for every coulomb of charge that flows through the battery, it will receive 9 joules of energy. But if it's just one little electron, it's only going to get 1.44 times 10 to the negative 18th joules. So I want to point out, it's such a small number, and these numbers are nuts. It's pretty much meaningless because charges are so small, technically they look like nothing. They're smaller than light itself, invisible to the human eye. And most of the time, everyday people, we're not going to worry about calculating these charges there. But in order to build modern electronics so that you can swipe on your iPhone, send your text, your tweet, it's all about knowing how to calculate precisely energy, electric fields, and electric potential in order to make modern life possible.